All right, so I think this is recording. In this problem, they give us two functions and they ask us 9 different things about these two functions. So let's begin with the first 3 of the things that it's asking. It's asking us to use these two functions to create a new function. In part A, through addition. In part B, through subtraction. And in part C, through multiplication. All right, so with addition and subtraction, we're going to need a common denominator. So I look at f and I write x plus 1 over 1. And I look to this function g and I see that it has a denominator of x plus 1. So if I want to add these two ratios together, I'm going to need to get a common denominator. So this first term I multiply by x plus 1 over x plus 1. So what do we get? Well, in the denominator, we have x plus 1 that we wanted. Now here, x plus 1 times x plus 1 is x squared plus 2x plus 1. And then over here, we're adding x minus 1. So the positive 1 and negative 1 cancel each other out, and we have x squared plus 3x divided by x plus 1. So we can't simplify that any further. So there's our new function, and they called this function f plus g. We could have given it any name. We could have called it h if we wanted to, but they chose. It's smart how you name it, because within the name tells us how it was constructed, how it was built. All right, so there's our answer for part A. Let's come in and work with part B now. In part B, I kind of want to do the same thing, because instead of addition, I have subtraction. So with this function g, oh, wait a minute, they've changed the order. G is this function, x minus 1 over x plus 1. And I'm subtracting this function f, which is x plus 1 over 1. I'm going to multiply that by the number 1, but I'm going to write 1 as x plus 1 over x plus 1. So now, with a common denominator of x plus 1, let's multiply x plus 1 times itself and get x squared plus 2x plus 1. Now, since you're subtracting that, you're not just subtracting the first term, you're subtracting the whole thing. So you need parentheses around that. So now in the numerator, we have x minus 1 minus x squared minus 2x minus 1. This is all over x plus 1. So we have a negative x squared minus x minus 2. And that's all over x plus 1. So that is, you could have called this function h or any letter, but it's smart in how they named it, because it tells us how it was constructed. All right. let's take a look over here at part C, this new function. You obtain it by multiplying these two functions together. F of x is x plus 1, and we multiply it by x minus 1 over x plus 1. So this denominator and this denominator cancel. And we have this new function that was made by multiplying the two old functions together, and we have x minus 1. Now, that, of course, that wouldn't be, well, there's restrictions on each one of these. Here, x couldn't be negative 1, or we wouldn't be able to add them together. Here, x couldn't be negative 1, or we wouldn't be able to add them together. And here, x couldn't be negative 1, or we couldn't multiply them together. So it is important to recognize that. But in the later parts, we find the domain of each one of these. All right, so let's do that. So we have this. I'm just going to erase all of this and move on to part D. Look how big the eraser is that you can make it. That kind of surprised me. I didn't know it would be that big. All right. So we want to find the domain of f plus g, f minus g, f times g, and we also want to find the domain of g divided by f, even though in the previous we didn't find an expression for that, we won't need to. Now you may be wondering why I grouped all of these together right here, and that's because even though they had different expressions, f plus g, g minus f, and f times g, the domain of all three of these are going to be the same, because to find the domain of these, we take the domain of f and we intersect it with the domain of g. So what I'm really going to start is to look at and find the domain of f. That's where I'm going to begin this problem. And the domain of f is all real numbers, because that's the default answer. The domain of any function is the set of all real numbers, excluding any values that cause division by 0. Well, I didn't have any variables in the denominator, so I didn't have to exclude anything. But you also have to exclude any values that would cause you to take the square root of a negative number. I don't have any square roots, so I didn't have to exclude anything there either. So the domain of f is all real numbers. When I look at the domain of g, it doesn't have any square roots, but it does have a variable in the denominator. And it's already simple enough to see that negative 1 plus 1 would cause division by 0, so we exclude negative 1 from the domain of g. So intersecting these two, to find the domain of f plus g, you have to be in the domain of f and at the same time be in the domain of g. Well, that's the set of all real numbers except negative 1. Negative 1 is not in both sets, therefore it's not in the intersection. So, like I said before, all of these have the same domain. The domain of f plus g is the same as the domain of g minus f, which is the same as the domain of f times g. And that even here, the order of subtraction, even if we had taken the domain of f minus g, it's all the same, because all of these take the domain of f and intersect it with the domain of g. Now remember, previously we've seen that u was the union, and that's the mathematical symbol for the word or. When you have this upside down u, that's the mathematical symbol for the word and. Like I said, you have to be in this set and in this set to be in the intersection. And the number that's not in the intersection is -1. So the domain for all three of these, my answer for D, E, and F is the same. It's from -infinity to -1, and from -1 to infinity. And that just happens to also be the same as the domain of G. Of course, that's not always going to happen. Now, let's shrink this up. So like I say, right there, that work was for all three parts, D, E, and F. By definition, for every problem, they are always going to have the same domain. But the domain of f divided by g, it could be the same as this, but sometimes it's different. Because not only do you intersect f and g together, you have this function g that's in the denominator, and you have to be concerned, you have to make sure that g of x is never equal to 0. Okay, so let's take a look at this function g of x. It's this ratio x minus 1 over x plus 1. And the question is could this ratio ever equal 0? Will this fraction ever reduce to 0? Well, guaranteed, if a fraction reduces to 0, it's because of the numerator. And if x were allowed to equal 1, you would have 0 divided by 2. And 0 divided by 2 is undefined. So we do not want x to be 1, as well as our previous answer that x couldn't be -1. So we're intersecting this domain intersected with the domain of g, intersected with the values of x that cause g of x to equal 0. So our domain for f divided by g is the set of all real numbers excluding -1 and excluding +1. And there's our answer for part I. I don't know where part G went. All right. Let's erase all of this and move on to find the domain of the function compositions. All right. And again, just like that I didn't need to find the expression for f over g, I don't need to find the expression for these function compositions because I have f and g separately of how they were built. So in part K here, if I'm finding the domain of this composition, I think about how this composition is built. And I like to think of it as an assembly line, where first you have the second function f, and you give it input from its domain. The output of it becomes the input for the next function. That was the function that was listed first. And its output is here. So for every input, we need exactly one output for this function. So any number that we put into f, for it to be in the domain of this composition G composed with F, we have to produce an output. Two things have to be true for that to happen. In order to have an output of F, X needs to be in the domain of F. And in order to have an output here of G, F of X, which is the output of F, needs to be in the domain of G. So what is the domain of F? It was all real numbers. So there were no restrictions as far as the input goes. What about here for G? Well, G takes on all input except a -1. Okay, so we have to make sure that F of X is never equal to -1. Because if we try to plug in a -1 into G, we get -2 divided by 0, which is undefined. The output is undefined, and we can't have that. So we have to figure out what input it was that caused an output of -1 and then prevent that from happening. So we have to temporarily take the function f, which is x plus 1, set it equal to -1 just to find out what x to avoid. So here it's easy to solve. We subtract 1 from each side and we get -2. This tells us that f evaluated at -2 is equal to -1. So what happens if -2 is in the domain? If -2 is allowed to be in the domain, then when f sees -2, it adds 1 to it, and you get a -1. When G is given -1, the output is undefined. So that means that we have to come back to the original input and say you can't have that. This -2 will not be related to any output. So the domain of this function composition, the domain of this G composed with F, is the set of all real numbers excluding -2. So from -infinity to -2, union -2 to positive infinity, that's the domain for this G composed with F, and that's our final answer for this part K. Let's erase it and do this next part, which I believe is the function composition just in the different order. Yes, we're finding the domain of F composed with G. So I don't need the expression for F composed with G. I just have to think of how you would build this function. You would build this function by taking input, something from the domain of G, and the output of G becomes the input for F, and the output of F is what we want. So this input would be related to this output, provided both of these are functions, provided everything is well defined. So the function G will give you an output provided that you don't give it a -1. If you try to input a -1, the output is undefined and we don't have a number to give to F, so it stops right there and we don't have an output here. So every input has to have exactly one output if it's a function. All right. So that's the first thing that has to be, is that the input can't be -1. Well, what about this output of G? Is there any restrictions on it? Because G of X has to be in the domain of F. But F is pretty easy-go-lucky. F has a domain of all real numbers. F will take on any value that you give it and produce an output. So there's no restrictions that F has, and the only restriction we have for this composition is that X can't be -1, which happens to be the same domain of G. So the domain of F composed with G, and sometimes that is, it's always going to be the domain of the second function plus any additional restrictions that you need to get through that second function. Here we didn't need any additional restrictions because the domain of f was all real numbers. So the domain of f composed with g is the same as the domain of g. And there's our final answer. All right, so is that it? I think that is. So if you have any questions, ask. If you've noticed any mistakes, let me know so I can edit the video, and I will talk to you later. Bye.